Okay, so let's see if we can't actually carry out a hypothesis test in a context that we're a little bit familiar with. So let's look at the relationship between square footage and house price, and that relationship is embodied in the alpha 1 coefficient. So from what we can intuit, the alpha 1 should be positive, right? We think that as square footage rises, the house price on average will rise. So alpha 1 should be positive, and that's even when we hold everything else in the model constant. So we're positing alpha 1 greater than 0. We put our pet belief, our a priori belief, in the alternative, okay? And this will be true for all one-tail tests for sure. We may have some exceptions when we get to a few two-tail tests. We'll talk about that later. Okay, so now we need a couple of things. Number one, we need to decide on what our test statistic is, okay? What evidence are we going to use to decide whether we reject the null or not? Intuitively, we think it should be the alpha 1 hat, right? That's the evidence that we get from our estimation process. But what we learned in the last module was that we can't standardize that because we don't know the actual standard deviation of the alpha 1 hat distribution. So we generate this thing called a t-statistic, which is going to be alpha 1 hat. So they're very closely related, the alpha 1 hat and the t-statistic, minus the alpha 1 value under the null, okay? So what do we mean by that? Well, we have a whole alpha 1 hat distribution. And if the null is true, for example, we know that 0 is consistent with a true null. So we're going to take that value and place it here, okay? We could have picked alpha 1 equal to minus 1, alpha 1 equal to minus 10. They would all be consistent with the null, but there's a reason why we want the closest value to h1 that we can get while still being consistent with the null. Okay, I'll try to justify that later. So the way we write this is we have alpha 1 hat, our estimate, minus alpha 1 under the null hypothesis. That is just 0. It's the proposed center of the alpha 1 hat distribution. So this is 0 in this case. And then we would like to divide by sigma, the standard deviation of the alpha 1 hat distribution, but all we have to work with is the standard deviation of alpha 1 hat, okay? And this is our t-statistic, okay? So the first thing we need to compute or to carry out a hypothesis test is a hypothesis, okay? The next thing we need is a test statistic, that's our t hat. The next thing we need is a decision rule, okay? And a decision rule is going to articulate the circumstances in which we will reject the null hypothesis. What will lead us to reject the null hypothesis? Well, intuitively and conceptually before, we were arguing that as long as the alpha 1 hat was sufficiently big, we would be led to reject the null in favor of the alternative. But now we have this slightly more involved test statistic, but if you notice the relationship between alpha 1 hat and t hat, they're pretty similar, right? So we're still going to reject the null hypothesis, but this time when the t hat is sufficiently large, okay? Now Studeman tries to give us a little bit of a break here and a kind of foolproof our decision rule construction. We're going to run into some cases where the reversed sign is here in the alternative, where we have an alpha 1 less than 0. And then we're going to be led to reject the null if the t hat is sufficiently negative, okay? And he's trying to help us sort of not get confused with our negative signs and bigger than and less than statements. So he's going to give us a decision rule. Okay, and again, a decision rule is just a rule that will tell us when we're going to reject the null and when we're not. That's kind of fail-safe. So our decision rule for a one-tailed test is if the absolute value of t hat is greater than some critical value and has the sign, that is the t hat itself, has the sign implied by the alternative hypothesis, we're going to reject the null. That is our decision rule, okay? So let's suppose that we draw a t that's positive. That is to say our alpha 1 hat is bigger than 0, so we have a positive t hat. So we don't have any problem with the sign. That's consistent with the alternative. If it's sufficiently large, okay, if it's sufficiently large, we're going to reject the null, okay? So we're actually looking at a t distribution now, so we could actually convert this into a statement of t's. I should really cross this off now and make sure that I'm focusing on my t hat, okay? But if our t is sufficiently large and has the sign implied by h1, we're going to reject the null. So what defines sufficiently large? Well, we want to look up the probability under the t distribution associated with our desired level of a probability of a type 1 error. And so if we just say we want to set the probability of a type 1 error relatively low at 0.05, we should now be able to find what that critical t value is, okay? How do we do that? Well, we go to our t table, okay, which is in the back of your book. We're conducting a one-sided test, so we're going to look across the top row of the table, and this level of significance is the probability of a type 1 error. So we've chosen a probability of a type 1 error of 0.05, that's equivalent to 5%. And now we have to look down the table to see how many degrees of freedom we have. And the degrees of freedom is the number of observations minus the number of parameters being estimated. So I have 1, 2, 3, 4, 5, 6, 7 parameters being estimated. I have 11 observations. 11 minus 7 is 4. So I'm going to focus on the degrees of freedom equal to 4. I'm going to choose the level of significance for a one-sided test equal to 5, and this is our special number. That is our critical value, 2.132. Okay, 2.132 is what's going to go in right here, and that's what would go right here. So if our absolute value of t hat is bigger than t critical, that is 2.132, and it has the sign implied by h1. h1 suggests that alpha 1 is greater than 0. So since this t is alpha 1 hat minus 0, if alpha 1 is greater than 0, we should expect alpha 1 hat to be greater than 0. We hope it is. So if our t hat is bigger than 0, and our absolute value of t hat is bigger than 2.132, we will reject the null in favor of the alternative. Now we can compute this, okay? This is basically alpha 1 hat, here's alpha 1 hat, divided by the estimated standard error, that's this 12.83, and conveniently Excel has already computed that for us, okay? So in this case, our conclusion is that the t-statistic in absolute value, 8.04, is greater than 2.132, and it has the right sign, it's greater than 0, consistent with our alternative. And our conclusion is therefore that we reject the null hypothesis in favor of the alternative. Okay? What have we just done? We have concluded that the positive estimate here on the coefficient for square footage is not due purely to the randomness of the sample or the peculiarities of the sample. We believe that fairly confidently we can conclude that the true alpha 1 in the population model is also greater than 0. We know that we'll be wrong in making that conclusion about 5% of the time in repeated sampling. Okay? Either we're right or wrong presently, but in repeated sampling we would expect to be wrong about 5% of the time in drawing that conclusion. So here's an example of a hypothesis test.